privilege to be here. I know there was another talk scheduled, so hopefully nobody here is expecting to have some energy efficiency. That would have been a good talk. Unfortunately, the individual couldn't make it to PyData. That happens occasionally. So I get to jump in. And I'm thrilled because I love to talk about Numba. It's sort of one of two topics I've been talking about over the past several years since kind of stepping down from active involvement with the NumPy community and just sort of playing a grandfather role, I suppose. It's great to see all the people here. I'm glad, but I know there's other interesting talks happening. I'm super excited to talk about Numba. I actually don't think Numba gets enough. I still hear people that haven't heard of it. Let's see in this room. Anybody not using Numba? Raise your hand if you're not using Numba. Yeah, perfect, exactly. See? Now that's fine. I mean, Numba isn't yet in everybody's DNA, but it really could be with just a few tweaks. It really is amazing. Currently, it can be used basically anytime you have analytics code that's array-like with scalars. So in typical NumPy situations, Numba will really help you write high-level code. Anytime you're trying to reach to C or Fortran, you often don't have to, and you can just go keep Python code and put a JIT decorator around it or a vectorized decorator around it, depending on how your code is organized, and get speed-ups very, very quickly. Those who have done it have been very grateful for its working. Now, there's still some caveats, still some things. It's not going to be, Python gets us a little lazy sometimes, at least the wrong word. It spoils us, right? Python just spoils us because it's so beautiful, and it can fit our brain, and we can just write code, and it sort of rolls off our minds into the computer. And Numba isn't quite like that all the time. It's not quite possible to just roll off your mind advanced analytics code and have it be as fast as you want and still as expressive and clear as Python. But some things are getting better. But a lot of things do get better when you go to compiled code. So there is a space of Python compilation, and it's important to talk about that space at least a little bit so you understand Numba isn't everything to all people. Numba sort of is an area of this space. It's just in time, a little bit of ahead of time. That's sort of in the experimental stages, but certainly on the roadmap is for Numba to be able to ahead of time compile and pre-compile modules, extension modules, but still it's relying on the CPython, libPython runtime, sort of not going beyond that. Now, Numba actually has a little bit of a segue, tiny segue, experimental mode into replacing, replaces the wrong word, but being able to create a shared module that doesn't rely on libPython and could be linked by something else. But that's sort of a different space. So it is not trying to be a just-in-time compiler that replaces all of your Python code. And I actually, something like Pigeon, which was shown by Dino yesterday. If you didn't see that, please look at the video. It's maybe not the whole video if you're not into compiler theory, but at least the front and the back. It's a really a cool proposition that I think holds some promise in helping bring JIT technology to more of your simple and Python code. Numba, most of the time, is trying to compile your code, and it's also not necessarily a tracing JIT, a JIT that tries to determine when you're calling it and then compile that which it sees as being called a lot of times. It actually is it's an intentional JIT. It's a JIT you say, yeah, please JIT this code. And then it will do that on import time or on call time, depending on how you call it. So it's a tool to be used to make your code faster, especially and with a focus on array-oriented, table-oriented code, which is very common in the analytics world. But there's some other actually interesting tools out there that are doing similar things. Pythran, Cython. Pythran sort of uses comments and then creates an extension module that you compile ahead of time. Rather interesting. It uses the C compiler in the end. It translates Python code to a C code that you then compile with the C compiler. Numba uses LLVM technology currently. And I like to show this slide because many people aren't, to people, compilers are something that somebody else does. But compilers are really a fairly straightforward concept. You are parsing something written in ASCII or Unicode to every compiler I've seen has some internal intermediate representation they use. Some internal, even if it's a set of data structures in memory and not formally specified, but there's something internally they're using. And then the compiler can basically focus on a parsing front end that produces this intermediate representation, and usually there's sort of several steps of translation in that intermediate representation to go make improvements, make optimizations, and then comes the back-end code generation. So with Numba, we're relying heavily on another project called LLVM to do that intermediate code generation to back-end, to x86, ARM. PTX is actually the code, it's the bytecode that NVIDIA uses on their GPUs, actually. So with LLVM and Numba, we actually get GPU calculations and GPU backends for free, sort of. So that's one of the reasons we're choosing LLVM, is to sort of try to unify and help unify CPU and GPU codes. But Numba basically just takes Python, and it doesn't even do any parsing, right? Python does all the parsing for us as well. So it's really kind of, it's the easiest compiler you could think of. It's just going from Python bytecode to LLVM IR. Now, even that requires a bit of, there's a lot of gotchas and questions and thoughts around that. And interesting problems in that space as well. But we're relying heavily on the work of a lot of people. So it's exciting, that's why we can make progress. But it also gives us a lot of room to do some interesting things. Very simple example, not something you would really do in practice, but you could basically decorate a simple function written in Python. This one just goes over a bunch of integers and calculates ratios. And you could calculate that in Python, do that in Python. It's a for loop. You wouldn't think you wouldn't typically do it that way. It'd be rather slow. But with the JIT, it translates that to low-level machine code and gets very, very fast results. What you see is a representation of LLVM intermediate representation. It's semi-readable. I mean, you have to, once you adjust your eyes and get the right glasses and kind of put a filter on your brain, then you can kind of walk through, okay, I get what's happening. I only have some extractions, some branching, and some comparisons. And it turns out that's enough to produce machine code on a large variety of machines. So that's what Numba does. Now, how does Numba work? Here's kind of the slide that goes into more detail about what Numba does to go from Python bytecode to LLVM IR and then ultimate machine code. So when you see a function at JIT, and that's the recommended interface, basically. There's two functions used out of Numba, JIT, and then we'll see later vectorize. And they're not, presently you don't have to call either one of them with arguments. You can call with arguments, and you'll see some examples of that later on. But the recommended approach is not to call it with arguments. So it doesn't. When you don't call it with arguments, then it does some bytecode analysis and constructs an intermediate representation, a Numba IR. This is basically an intermediate representation that Numba can use to then inject type information that it acquires once the function gets called. So when you define the function with JIT, it basically returns this intermediate delayed function evaluation. It's kind of it replaces the function with a object that when it gets called will evaluate the function arguments passed in. Now you know the types the function arguments passed in. When you don't have any functions, any arguments passed in, then that A and B, they could be anything. It could be integers, floats, arrays, you don't know what it is. And so therefore the code that gets generated could be quite different. It's sort of like templating. It's very, very similar to templating, in fact. So you create this sort of uninstantiated, half-evaluated dynamic thing. When you call it, now it has type information. And then it uses type inference. The Numba IR has some unannotated information that, hey, I don't know what the types of these things are. The type inference takes the types of the inputs, all the functions you're calling, tries to determine all the types of the intermediate variables inside the function as well as the output return types. That is not always possible, as you can imagine. Python is very, very dynamic. People call all kinds of funny modules, functions that nobody understands, that Numba certainly doesn't understand. And so if it doesn't know what is returned, it just sticks a generic PyObject. It knows about the PyObject type and just sticks generic PyObject. And effectively, when you can't do type inference on everything, then you're really back to the Python CAPI, or the Python runtime, just doing function calls on objects, exactly like the runtime works with Python. So you won't get any speed up if it can't do type inference. That's essentially, and any people that struggle with Numba not giving them speed up, it's because the type inference didn't succeed. And why didn't the type inference succeed? Likely because you called some function it doesn't understand, or some operation potentially doesn't understand. And we've been sort of working pretty hard in the Numba team to make Numba understand math functions, all the the scalar working syntax, and a lot of the NumPy API. So if you even use NumPy, you can now use NumPy inside a Numba function, and it won't call NumPy. It'll actually just generate code for you that does the same thing as NumPy. Basically understanding the NumPy code. So it makes a sort of a nice tool for the NumPy user and the NumPy stack. So after type inference, then it rewrites the Numba IR, inserting type information, And then it takes that information and lowers it to closer to LLVM IR, where some optimizations occur. And then finally, it ejects that IR I showed you, that complicated LLVM IR. And at that point, LLVM takes over, calls the JIT of LLVM, which takes that IR and produces machine code, and that machine code is then executed. And there's potential for some caching along the way, so you don't have to, once you call it with a certain number of types, it caches that machine code result and doesn't recompile every time you call it until you exit Python and enter Python back again. The caching currently is not persistent, it's only in memory. So you pay the cost of compilation once every time you call the function. So the Numba JIT it's a function level JIT. It's not going to try to inspect your code. There is one area where it does something a little bit magic, but mostly it's just going to inspect your code and compile the machine code what it can. Now it has to generate actually two functions. When you have the JIT decorator around a function, think of what's happening. There has to be a Python entry point to that function. There has to be some Python object that is an entry point to the machine code. So basically two things are generated. One is the Python object that it calls, and the other is the machine code that it represents that function. So when you call the function, when it's fully typed, with full type inference, you have those two mental things, those two concepts floating around. Now, most of the time you don't have to think about all this. But when you do is when you're really trying to kind of get to the hard, maybe something doesn't go right, you're trying to figure it out, then you have to have a little bit of a mental model that is accurate, that is relatively consistent. So what does Numba support currently? The Numba team's working really hard, and incidentally, Numba was a project I got to spend a little bit of time on in 2012, and all the code I wrote at that point has since been rewritten about 3 times, and by a very strong team that is actually consisting of about 4 or 5 people. So everything I'm talking about is done by them. It's a fantastic group. We're always looking for open source contributors. It's a fully open source project, and anybody interested in getting involved with this team is welcome to join. So Numba supports Windows, OS 10, and Linux, and that means we're compiling LLVM on all those machines and making it available so that each of those, it's 32 and 64-bit x86 CPUs and NVIDIA GPUs. There's preliminary, there's on the roadmap support for ARM and support for AMD CPUs and the CPU-GPU combinations, but that's not yet in released versions. It does support Python 2 and 3. We work pretty hard to make sure that the code is the same across those 2 installations. And then NumPy versions, it does require a NumPy version, 1.6 through 1.9. A lot of value a lot of people get out of Numba, especially Windows users who have a hard time not having a C or C++ compiler, is it does not require one. So you install Numba, and you basically have the equivalent of a compiler without having to go and install one. So you get the ability to write machine code just with Python syntax and the Numba runtime. And it does not replace the Python interpreter. You still need the Python interpreter. You still need NumPy. It doesn't replace NumPy yet either. You still need NumPy. And then the other flip side of that is all of your existing Python libraries still work and are still available. You don't have to switch off from doing that. You can just insert Numba into your workflow and see if it helps you. Numba, you'll often hear us talk about 2 different modes, and I got close to describing those modes when I explained that the type inference, if it doesn't know what it is, will keep object mode. It'll keep an object on those types. Anytime you have a function that you've JITted where the type inference did not know what it was or inferred that it's an object, you're in what's called object mode. When you're a Python object, naturally, we can't get rid of the Python runtime. We rely on it to do the operations. So it's called object mode. And effectively, you're not going to get significant performance improvements. You might get a few percentage points because you've gotten rid of the loop, the eval loop, the switch statement in Python, but a lot of times, no, that's not true. And you occasionally might even get a little bit slower. So what we're going for with Numba is to try to get you to no Python mode. And that'll happen automatically if it can. There is something called no Python mode where you can, it doesn't change anything. It doesn't change what Numba's trying to do. All it does is change what Numba tells you. It says, if you ask for no Python mode, then it says, give me an error if you can't do it. Don't just go to this other object mode. Because there's just 2 use cases. Right? Some people want to add the JIT and then have it keep working even if it didn't get faster. They don't want suddenly their code to break. Other people, they're trying to do hotspot analysis, really trying to develop. They want to know if it's not working so they can fix it. So you have those basically those 2 concepts, those 2 modes. No Python mode, what you get is machine code. So you get out bits, you get out binary strings that operate at the speed you're controlling the machine. You're no longer relying on live Python, you're no longer relying on anything, therefore you're not getting any of the benefits of that dynamic live Python either, but you're able to go as fast, usually within 25% of the speed of C or Fortran. So how do you use Numba? Numba currently, it would be awesome if you sort of had this Numba command line, you sort of Numba, a lot of people ask for this, Numba, give them my Python script, and it all just magically goes fast. Yeah, that'd be cool, right? The challenge is that, like I said before, Python is very dynamic, and it's unclear what you've done, and you probably have taken advantage of that throughout your code using dictionaries and sets and lists and all kinds of cool features that make your code expressive. And Numba is not going to be able to do anything with all of that. There's a whole list of features of Python that are not supported by Numba. Numba is really a subset of Python that can be optimized. So to use Numba, it's really about creating a realistic benchmark. The unit tests are typically not the right benchmark. They typically you're not going to get the speed up you're looking for because it's a different purpose. So having some kind of benchmark test cases, run a profiler on those benchmarks, and then identify those hotspots. Now, I know from experience, and Numba's been around since early 2012, but not really usable till early 2013. And then it's gone through a couple of changes in 2013. Since 2014, it's been pretty stable. The same code base, the same. It's been moving forward more iteratively, more slowly. A lot of backward compatibility since January 2014. And since that time, we've used it in lots of projects. We've used it and done exactly this, and really helped a lot of people go from code that's running slow to getting 2, 10, even 100, 500x speedups in their code bases just using this process, basically. So with Numba, you can really get a long way, and you can get like 1,000x speedups if you start taking advantage of the GPU, which is a little harder, still not quite as easy as taking advantage of the CPU at this point. So identify the hotspots that could potentially be compiled with maybe no refactoring, but usually there's a little bit of refactoring required, and then use JIT and vectorize in order to get those critical functions to be machine code. And then rerun the benchmark to see if there's a performance improvement. So we're going to talk about some of the Numba features here and kind of give a whirlwind tool of features. The text here is inaccurate, a fast presentation put together last night. So the basics of Numba are just using @JIT on a function. Here's a simple example that basically extracts out is-nans, so nans from an element from an array. It takes an array, and now I'm illustrating a couple of things here. Numba now has, as of 0.20 release, a memory allocator. So you can actually allocate memory in no Python mode outside of. And there's actually a little reference counting mechanism that's uses intrinsic atomic instructions provided by many processors to actually manage that and connect with the Python memory management when it goes back to Python. So it gives you the ability to create arrays inside of your no Python mode, which is very, very nice. And lots of features fall out of that, actually basic functionality. And in the future, including JIT classes will come out of that too. So here I'm creating a new array inside my no Python mode function, and then notice how I can loop through the array using natural Python syntax. I just go for element in X like an iterator, but underneath the covers it generates machine code to do that in a way to iterate the pointer through the array elements. And then I do a check to see if it's a nan, and if it isn't, then replace the out index, sort of grab all the functions that are not nan into a new array. So that's what out does. That's what this little function does. And it's similar. You can get the same effect in NumPy by basically doing masking selection on a regular array. So basically, I'm implementing that masking selection on a regular array with just a function I've compiled with Numba. And you can see that in this particular case, I'm getting somewhere 2.5x speed up on the result. So, and that's usually pretty typical. We see on NumPy is it's fast, but it's not always optimal. There's it's a general code base, and so it's not always particular for your specific problem. You can get roughly somewhere between 1.8 and even up to 10x speedups by writing little snippets of code even over the NumPy code base. So that's why, again, the performance optimization is really critical because you don't want to go be optimizing all these sections of code in your overall workflow that aren't getting called that much. It might be fun, might be enjoyable, kind of a nice pastime, perhaps better than playing Minesweeper, but not going to necessarily get you a faster overall code base. So it's very simple to use. Now, I don't have to say no Python equals true. I could have just said @JIT. The only reason to say no Python equals true is if I want the compiler at function declaration time to tell me, hey, I couldn't, or excuse me, it'd have to be a function call time because I haven't specified any types. So at function call time, when I provide some types, it'll tell me I don't know how to infer the rest of the types in here, so I can't go to no object mode, sorry. And it'll raise an error. Right? And sometimes that's helpful, and sometimes it's not. And so that's what that flag does, is if you want to be told when you call it that it can't do it, then put the no Python equals true. If you don't, then don't do that. You have a question in the back? That's a great question. Yeah, the question is, he sees the timing, and it's a best of 3, it's multiple loops. So he's asking, how much time does it take the first time you call it? Because, of course, what happens the first time you call it with new types, it's going to compile it. And the answer is somewhere between 100 microseconds to 10 milliseconds. But obviously, the more complicated the code that's being compiled, the longer that can get. And if more optimizations are done, the longer that can get as well. There is some, LLVM is not known to be a fast compiler. It's sort of been optimized to be a static compiler with Clang and other front ends. Julia uses it well, so there is some pressure trying to make it faster. And there are improvements being made in that direction, but historically it's not the fastest JIT out there. So, but in the use cases we've are applying Numba, which is sort of large or computational analytics approaches, typically it's well below the runtime of that function. So even the first time you call it, it's going to be within 10% or less of the overall function result time. But it can make a difference. And so it is important to understand the first time you call it, it will have that compilation time. And we are looking at ways, as that becomes a problem, you can then start caching things, generating shared object code, generating layers to speed that up. But so far, that hasn't been done in the project itself. Yes, another question. Yeah, that's a great, he's asking about keyword arguments, default values, keyword arguments, and what does it do in that case? Does it sort of pre-generate perhaps a... Does it pre-generate both the generic and specifically for those? Yeah, that's a fantastic question, and I do not have an answer for you. I know that it's possible that actually keyword arguments are still not supported. Right, it may be that you can't do that, actually. However, I need to check that because I know that was on the enhancement list and something that's been of interest for a while. So I'll have to get back with you. I don't know for sure exactly what the status of that is. It may be that, let's say for now, that keyword arguments don't work. And if they do, then you'd have to understand there'll be some technical details around how that's implemented. So I guess the annotations that I could have provided earlier. But I'm really excited about the allocation. Earlier, you basically could not allocate arrays in Numba. You would basically have to pass in any array you wanted to fill in. And now you can. And so you can have this, it opens up a lot of doors. Being able to sort of doing that array allocation and the reference counting and the memory management necessary to handle that array allocation is actually a pretty big deal. We're pretty excited about what that's going to imply in the coming months. So one thing about using this JIT is you can then call other JITted functions inside your function that's JITted. And when you do that, it will not go through Python. You're just making a machine code function that then another machine code function is calling. And in fact, LLVM will even do inlining of that function if the function is simple enough. So here's an example where the clamp function, which is just a simple if statement check, that gets inlined into the calling angle in the angle between function when it gets called. So because of that inlining and that the other optimizations of LLVM will often give you speed up. So if you compare this code is JITted and it looks like NumPy code, right? You're calling NumPy arccos and all those things, but it's not actually calling NumPy when it's in no Python mode. It actually is doing the work that NumPy would have done, but in a different, using a compiled code. It's about 10x faster in this particular case. But one of these functions doesn't get inline because it's a little more complicated, and the other one does. Now, one thing I love about Numba, you have a question in the back. Yeah. There's basically some environment variables you can set that basically give you more information about outputs. And you can also get the LLVM produced by the function and even the machine code produced by the function. So there's straightforward interfaces to taking the function that's been called and getting the LLVM out of it that it uses. So that's how you would kind of inspect and look and see and notice. There may be other ways, but I know there's that way. The question was, is there a way to get to know that something's been inlined or not? Thank you. So ufuncs, how many don't know what a ufunc is? We'll see if you're brave enough to admit. Awesome. You guys are awesome people. It's always good. So a ufunc is called a universal function. It's the basic mapping function in NumPy, but it's kind of magical because there's a lot of work done to do a few things. One is type coercion, so I can have an integer and a float together coming to a ufunc, and NumPy will coerce them to a common type that it then can find a low-level routine that works for it. So there's all this machinery around the ufunc object in Python. It's actually written in C, but it's a Python interface that lets you attach low-level routines that iterate, that do very simple things. They just element-by-element iteration doing some function like a sign or an add or a divide, or we'll see later even fancy special functions. But it does things with the arguments. The type coercion, it does broadcasting. Broadcasting means I can put a scalar with an array, and it'll take that scalar and array and broadcast the scalar across the array. I can take an array and a matrix, and it'll convert the array to a matrix with the right elements, so I can combine those two element by element. All that's done for you with ufuncs. So I always wanted, one of the first things I was doing when I was starting the SciPy project, I just wanted more special functions. I wanted lots of functions for you as ufuncs. And they were kind of hard to build. You had to do it in C. You had to construct these low-level functions. I always wanted to say, here's a Python function. Let's make that the kernel in a ufunc, and it turned out I had to write a compiler to do that. So it wasn't available. There is a vectorized function in NumPy. There's a numpy.vectorize, but it isn't what I wanted. It's okay, at every element here, I'm gonna have an object mode, and I'm gonna go back into the Python runtime and call the function, then put that back in NumPy. And that can kind of be a drag when you've got, a billion elements in your array, and you're going back into Python mode and doing something every time. With Numba vectorize, we can actually do this. We can build the kernel that is called by the NumPy, by the ufunc machinery. So all that machinery just starts up front and then hands it over to this precompiled function, and off I go. So you can kind of go be crazy with yourself and figure out all kinds of ways. If you have a mapping, if you have some way to think about, here's my array or here's my data, and I just want to do some mapping of every element of that array. As complicated as that mapping might be, and as many other arguments that it might need, you can build that. And then you can apply it to a large data set. That's what ufuncs are. They're the kernels that get applied to a large data set. So add is the simple one. Right? Add is a ufunc, and you can apply it to two arrays, and element by element, it'll do that addition. Here is the element by element calculation. It actually was motivated by Hearthstone. I'd never heard of that game, actually. Anybody here played Hearthstone? Okay. Apparently, this is from Stan Siebert, lead developer on Numba, and he was basically wondering why he kept losing. And so he was trying to just Monte Carlo simulate kind of the process of, and I basically, this game is you have a win probability, number of max wins, number of max losses, and then you go through and generate a random number. It exits as soon as you've basically had the max number of wins or the max number of losses. And then it returns how many wins, right? So you're basically trying to figure out what's the likelihood of this happening. Interesting function to call. It shows that there's a loop here in your inner loop of every element, and there's also random number generation using numpy random.rand. I should caveat here, you can use np random.rand in a no Python context. It generates machine code for doing a random number generation, but it's not thread safe yet. So, and vectorize does implicitly, if it's not object mode, NumPy will release the GIL. It'll release the global interpreter lock and call this in with, so if you call this with multiple threads, you might end up with a challenge. Or might not, it might work just fine, but you might have a problem because it's not guaranteed to be thread safe. So But it's fairly straightforward code, and then you can apply it. If you look at that sim input, np-tile, all it's doing is generating this 100 points from 0 and 1, and then replicating that 5,000 times. You end up with a 5,000 by 100 matrix array, and you can then calculate on that array this game wins function on every element of that array. Broadcasted against 12 and 3. So 12 is the number of wins, 3 number of losses, and you're inserting this sort of win probability function. Now, you could just do this with 1. This is just illustrating you could do a bigger job. And it doesn't take very long, 50 milliseconds for that kind of simulation. And you could generate that win probability curve and see that, oh, I can see why I don't do so well. My win probability has to be really, really high before I get sort of biased down pretty low, expected number of wins before the game ends. And pretty unlikely that I'll actually have 12 wins, or the max number. So ufuncs, this to me was a big deal. This is sort of like one of those moments in your life when you sort of have a wish and desire for many, many years, and it comes to pass, right? After a lot of work and a lot of help and a lot of other people, LVM, Numba, a lot of work had to come to play. But what it definitely illustrates, so a lot of things that motivated me when I started the SciPy project in 1999, early on, and Special was one of the first things I wrote, was I just wanted more stuff available to the Python user. I wanted Python users to be able to do optimization, integration, special functions. I just wanted them to have all the capability that they might get in something like MATLAB or IDL or PVWave or any number of these applications. So I was very motivated. I was also very young. Didn't care about money. My wife was patient with me. Our kids were young, so we didn't have to worry about some of the things we have to worry about now. But I spent a lot of time just trying to push this. If I'd had Numba, if Numba had existed, SciPy would be completely different. It'd be completely different. It would just be completely different. I mean, because we could do all of this, we could do a lot of things just in Python itself. And the things we would need as library form could just be linked to, and I guarantee everybody would be happier. The PyPy people would be happier, the Python people would be happier, you would be happier, things would be faster, there'd be more things to be thread safe. So I say that because I think Numba's a big deal. And I say that with all the history of all the effort that I put into NumPy and SciPy, that I think Numba provides us a framework and opportunity to create things that go bigger and broader and go beyond what we have currently in the PyData stack. So I'm very excited about it. That's why I invest so many resources in it. I think it has a lot of potential. So I'm just illustrating a case study of translating something from SciPy using Numba and showing the result. So here is the Bessel function. I just went to the C code that was wrapped with SciPy, and I translated that C code to Python code. It does the same algorithm that CFES is doing, and it's basically this PyData approximation, if you know what that is, of a common function. It's got these polynomials, constants you have to insert, and then some polynomial evaluation code. So that's the code, and I just pull it from CFES, wrote it in Python, fairly readable. You can even go in there and start arguing about, well, I think it ought to be this length, or I think we ought to put a different approximation here, or I think we should change this or this. A lot more collaborative, a lot more ability for a lot more people to kind of insert themselves and go, maybe we should fix this and make it better. That's one of the advantages of Python, is it brings more people together. It doesn't sort of separate the sacred algorithm writers from the people that know what understand maybe the math. So. Now you don't actually need that type inference anymore. Previously in Vectorize you had to give it what types to generate it for, but Vectorize now there's a shim that'll do that dynamic compilation on the fly and addition and insert low-level routines for you. So you don't need any of those decorators anymore. You can just say @JIT and @Vectorize, and the result is this vectorized Bessel function that turns out to be the same speed, roughly, a little bit faster in this case, but roughly the same speed as the SciPy J0 function. So I think that's cool. I think basically, that's why I say all the code, SciPy would be much different if this had existed. I'd have spent more of my time writing Python and less of my time linking Fortran. And I would have been happier, and we all would have been happier. But now we could have been moving this to the GPU, we could have been doing a lot of things. So the word's starting to get out, and we had a recent Numba mailing list where somebody else was starting to they got 2x speed up by taking their Python code that they'd written. It was a spatial hierarchy function inside of SciPy, and they just took the code and removed all the type annotations, made it more looking like Python, and then just put JIT around things. They did have to make a few minor changes to the code, Like I said, it's not perfect. Numba doesn't just take everything. But he was really pleased. It was only a few minor changes, slight differences in the way he approached it. And then it was 2x faster, the result. So what that means to me, as soon as the Numba's ahead of time compilation, where you can actually use Numba to generate a shared object you can then ship to somebody else, as soon as that moves beyond experimental stage, you can legitimately use Numba to create a library, which then doesn't require Numba for the person you're giving it to. Maybe it might require a Numba runtime, right? I'm not going to claim that it might not, but will basically require a smaller install. So SumPy and NiPy would look very different. Both SciPy and NumPy actually would look a lot different. So Numba is actually getting some more Pythonic things, actually. It's growing. One of the complaints is that it looks a lot like Fortran. It does. You sort of have to write your code like NumPy people would or Fortran people would, and they're the same people, so they're happy. But it's you miss some of your high-level things, and those are slowly being added. Generators are now there in Numba, so Numba you can basically create a generator function. And then it's faster than just doing it in Python itself. So here's just a simple example of using a generator to basically make an iterator. But it's all in Python. Is that 2 minutes? Thank you. So releasing the GIL. A lot of people fret about the GIL in Python, and for some good reasons. Some of their complaints are good, some of them aren't. And in the PyData stack world, we've actually been sort of like, well, whatever, I'm not sure what the problem is. We release GIL all the time. Right, we have multi-threaded code all the time. Not every PyData function does, but it's sort of like this mantra. There's at SciPy 2015 this year, there's like, release the GIL, everybody. It really does, it makes things nicer on multi-core CPUs. NumPy does it. NumPy takes a lot of pains, actually, to release the GIL when it can. SciPy does it most of the time, quite often. Scikit-learn now does it. Pandas is going to do it or now does it. I know there's some effort involved in making it release the GIL when it can. Python makes it easy to release the GIL, and Numba makes it easy as well. It's a very simple thing. You do have to be intentional about it, though. It doesn't just automatically release the GIL, because you do need to make sure your code's thread safe, or else it's going to be trouble. I mean, there's actually some benefit to having Python not release the GIL. It makes it much easier. You're not always writing multi-threaded code. You have to be intentional about writing multi-threaded code. But when you know you can, and there's many cases where you can, on the function being called from Python, you just put no GIL equals true. Notice in this example, I don't have to put no GIL equals true on all the functions being called, only on the function I intend to call from Python. So the intermediates, the GIL's already released, so it's already in, there's no global interpreter lock, those are already happening in the thread. But you better make sure that your code is thread safe. Not using globals is usually the problem. Not updating any arrays that other threads might be trying to update at the same time as well. So there are some caveats, but releasing the GIL, and in this example, we're using the really nice concurrent thread pool executor from Python 3, plug for Python 3. It's got a lot of neat features and cool things. The thread pool executor in Python 3, and you can see you get not quite linear speed up. Very, very simple to release the GIL, get thread, actually have calculation functions going to multiple threads using Numba for a subset of Python. Many people didn't, I'm sort of amazed that some people don't realize this, but CUDA Python is in Numba. You can actually write code for the GPU in open source Python. It's completely open source. You can all do it. You do have to have a GPU. And you do have to be willing to learn some CUDA, right? It's CUDA Python, meaning that you still have to understand CUDA a little bit and what it means to take code, write a kernel, and what that means on the GPU. You'll look in there and you'll see CUDA thread blocks, CUDA thread, CUDA block dim, okay? And if you don't know CUDA, it's like, what is all that stuff? And you have to kind of be clear about what that is. You're writing a kernel, you're writing a little function that's gonna run on 1,000 virtual threads or 10,000 virtual threads. So you have to basically know what you're gonna do on each one of those threads. And so that's all that's happening here. It's a very simple scaling function. I'm scaling a destination and a source. I can't allocate arrays in CUDA. That's one thing that's different. So there's a CUDA JIT. It's from Numba import CUDA, CUDA.JIT. And then I have to call it differently because I have to give the GPU an understanding of how many threads per block, how many blocks per grid I intend to use this on. So the interface is a little bit, there's some effort there, but with not very much investment and with Python syntax, you can write GPU code. And a lot of people have been doing it to great effect. Here's an example of a Black-Scholes calculation done on the GPU. I'm not going to go over that detail, but you can basically see 9x faster than the CPU code and about the same speed as CUDA-C. So now CUDA is open to Python users. And you can just have a GPU on your machine and it's a little bit of fearlessness and willingness to experiment, and you can do a great job. All right, so we are out of time, but there's some other interesting things. CUDA simulator, generalized ufunc, call types, preliminary support for types that understand the buffer protocol. Numba annotate, very good idea to understand what's going wrong. Those are all there. And then list of what doesn't work, yield from, generators there but not yield from, recursion, exceptions. There's some of these things that make Python really nice that you have to take a subset in order to use Numba. But that subset is growing and growing, and for array-oriented code with arrays and scalars, works really, really well and gives you a pretty good result. And I'm excited about what's coming. JIT classes, that will be interesting, open a whole new world for people to create basically little record arrays and record classes that can then go all over the place. More coverage than PyAPI and bug workflows and so forth. Thank the Numba team. Again, I was very excited about Numba. I'm a champion of Numba. I push Numba wherever I can. But there's a big group of people that actually make this all work. Graham, Antoine, Sue, John, Graham, Oscar, Jay. Thanks to all of them. And any of you that are using Numba and are giving us reports. All those people are very interested in your success and failures. So if you fail, tell them, and you'll nerd swipe them and get them to work for you. So please join us. And thanks. Appreciate it. Nice to be here.